In this section, we will be looking at nuclear magnetic resonance, known as NMR. NMR is a technique that makes use of the magnetic properties of certain nuclei, and there are two main types that we most commonly use: proton NMR, which is looking at hydrogen, and carbon-13 NMR. In this module, we will only be focusing on proton NMR. By the way, it is called proton NMR because the nucleus of hydrogen-1 consists of just a single proton. First, let's look at the principle behind NMR. The nuclei of certain atoms have a property called nuclear spin. The nucleus of an atom is charged, and a spinning charge would generate a magnetic field. So we can also think of the nucleus of an atom that is spinning as a kind of magnet with a north pole and a south pole. When an external magnetic field is applied to the nuclei, this nuclei can have two possible spin states. The nucleus could spin in a way that is aligned with the applied magnetic field. This would be the lower energy state. Or the nucleus might spin in a way that is aligned against the applied magnetic field. This would be a higher energy state. When a nucleus in the lower energy state absorbs energy of a specific frequency known as the magnetic resonance frequency, it can be transformed into the higher energy state. This frequency of electromagnetic radiation falls within the range of radio waves. So among the different spectroscopic methods that we have been discussing, such as UV, visible, IR spectroscopy, and NMR, NMR uses radiation with the lowest frequency. This diagram illustrates the lower energy state. So when an external magnetic field is applied, the magnetic field of the nucleus aligns with the external magnetic field. Where the nucleus absorbs radio frequency of a specific wavelength, the spin can be changed so that the magnetic field of the nucleus opposes the external magnetic field. This diagram shows the components of an NMR spectrometer. The sample is placed in a very strong external magnetic field. It is then subjected to frequency from a radio wave source. The results will then be detected and interpreted. This is an example of how the proton NMR spectrum looks like. The hydrogen atoms in the chemical structure are detected and give rise to the different peaks. The x-axis is chemical shift and the units are ppm. The peaks that appear on the right side are said to be more upfield. These belong to protons that are more shielded. The peaks that appear towards the left are said to be more downfield and belongs to protons that are more deshielded. Let's look at what shielded and deshielded means. The nuclei of atoms don't just exist alone, they have electrons surrounding them. These electrons surrounding the nuclei will shield the nucleus from the external magnetic field. So if there is a higher electron density surrounding the nucleus will be more shielded from the external magnetic field. And if the electron density around the nucleus is lower, then it is said to be more deshielded. The electron density around different nuclei is not the same. For example, a hydrogen atom might be attached to another atom with a similar electronegativity as it, and the electrons would be shared more or less equally between the two atoms. But another hydrogen atom may be attached to a more electronegative atom which pulls the electrons closer towards itself. This hydrogen atom would then have a lower electron density surrounding its nucleus because the electrons are pulled further away from it. So for this hydrogen atom, the nucleus would be less shielded. So let's take a look at the chemical shift scale again. The x-axis represents the chemical shift of the proton that is observed relative to a standard called tetramethylsilane, or shortened as TMS. The chemical shift value is reported in units of parts per million. The peak that corresponds to TMS is always assigned an arbitrary value of 0 ppm. Then all the other protons in the spectrum would then be referenced to the TMS peak. The chemical shift scale increases from right to left. So 0 is on the right and larger numbers on the left. And for most compounds, the typical range would be about 10 to 12 ppm. Also, to recap, the right side is called upfield and the left side is called downfield. The peaks that appear upfield correspond to the more shielded protons, which have a higher electron density surrounding them. The peaks that are more downfield correspond to the protons that are more deshielded, which means that they have a lower electron density. This is the chemical structure of tetramethylsilane, TMS, which is used as the reference standard in NMR. All of the hydrogen atoms are bonded to a carbon atom, which is bonded to silicon. So all of the 12 hydrogens in this TMS have the same electronic environment, meaning they have the same electron density. Since there is only one electronic environment for all the protons, this gives rise to only one peak in the NMR spectrum for TMS, and it is a very strong peak because there are 12 hydrogens. The peak that corresponds to TMS on the NMR spectrum is assigned a proton shift of 0 ppm, and almost all organic compounds will produce peaks to the left of TMS. Let's take a look at the proton NMR spectrum of methanol. The peak at 0 ppm corresponds to TMS. Methanol itself gives two peaks on the NMR spectrum, one at about maybe 3.6 ppm and another peak at around maybe 4.8 ppm. If we look at the chemical structure of methanol, these three hydrogen atoms are bonded to the same atom, and so they are said to be in the same chemical environment. These three protons give rise to this peak. There is also another proton bonded to O, and it gives rise to this peak. The oxygen atom is more electronegative compared to the carbon atom. So in this OH bond, the oxygen atom would pull the electrons closer to itself and away from the hydrogen atom. So this hydrogen atom would be more deshielded. Therefore, the peak appears more downfield. In comparison, the carbon atom doesn't really pull the electrons away from the hydrogen atoms. So these hydrogen atoms are more shielded as they have a higher electron density surrounding them. And you can see that the peak appears more upfield. Hydrogen atoms that are bonded to different atoms and functional groups would produce different chemical shifts on the NMR spectrum. This table of chemical shifts is provided in the exam. Let's look for the chemical shifts corresponding to the protons in methanol. The hydrogens on CH3 next to the OH group is listed in the table under alcohols. The expected chemical shift is between 3.4 to 4 ppm. This is consistent with the NMR spectrum that we saw earlier. Now, how about the H atom on the OH group? The hydroxylic hydrogen atom has an expected chemical shift ranging from 1 to 5.5 ppm. We notice that this is a very broad range, but the OH peak on the previous NMR spectrum of methanol falls within this range. Now let's look at the size of the two peaks in the NMR spectrum of methanol. We can see that the peak corresponding to the hydrogen atoms in CH3 is higher than the one for OH. The area under the peaks actually gives us relative information about the number of protons. So the area under the OH peak and the area under the CH3 peak would have a ratio of 1:3. Now let's interpret the proton NMR spectrum of another compound, ethanoic acid. If we look at the structure of the compound, we can see that there are hydrogen atoms in two different chemical environments. There are three hydrogens that are bonded to a carbon atom, and there is another hydrogen in the COOH group. Let's take a look at the table to see what chemical shifts we can expect for the CH3 hydrogens. For carboxylic acids, the hydrogen bonded to the carbon next to a COOH group would have a chemical shift of 2 to 2.6 ppm. We can see that the chemical shift on the NMR spectrum is consistent with this range. The hydrogen on the OH group in carboxylic acid is also in the table and is expected to have a chemical shift of between 10.5 to 12 ppm. This is also consistent with what we see in the NMR spectrum. Now let's take a look at the sizes of the two peaks. When we talk about the sizes of the peaks, we are not really referring to the height of the peaks, but the area under the peaks. The ratio of the area under the two peaks would be 1:3. This is because there are 3 hydrogens in the CH3 group and 1 hydrogen in that COOH group. So to reiterate, to interpret a proton NMR spectrum, the number of peaks in the spectrum will tell you the number of different environments the hydrogen atoms are in. The ratio of the areas under the peaks will tell you the ratio of the numbers of hydrogen atoms in each of these environments. And the chemical shift, which is on the x-axis, will give you important information about the sort of environment the hydrogen atoms are in, whether it is more shielded or deshielded. You can also refer to the table of chemical shifts to tell you the approximate range of chemical shift that you can expect to find those hydrogen atoms in. Now let's take a look at the chemical structure of a compound, methyl acetate. Looking at the structure of the compound, how many peaks do you think will appear in the proton NMR spectrum of methyl acetate? Refer to the table of proton chemical shifts in NMR and identify the approximate chemical shifts of the peaks. Press pause to think through this question yourself, then press play to continue with the answer. Looking at the chemical structure, we can see that there are actually two different sets of hydrogen atoms in two different chemical environments. This is an ester. 3 of the hydrogen atoms are bonded to a carbon, which is next to a carbonyl group. The other 3 hydrogens are bonded to a carbon that is next to an oxygen atom. Let's first look for the chemical shift corresponding to the hydrogens on a carbon next to the carbonyl group in an ester. In the table of proton chemical shifts, we can see 2 entries for esters. One is for the hydrogen that is bonded to the carbon next to the carbonyl group, and this has a chemical shift of between 2 to 2.2 ppm. The other one is for the proton that's bonded to the carbon atom next to the oxygen atom, and this hydrogen has a chemical shift of between 3.7 to 4.1. Since both groups have 3 hydrogen atoms, the ratio of the area under the peaks should be 1:1. So this is the proton NMR spectrum of methyl acetate, and as we have predicted earlier, we see 2 peaks. The peak at 2.05 corresponds to the CH3 group next to the carbonyl group, and the peak at 3.662 ppm corresponds to the CH3 group that's next to the oxygen atom. There is low resolution NMR and high resolution NMR. For low resolution NMR, the information that is provided by the NMR spectrum would be what we have already discussed earlier. So to recap, the number of peaks would tell you the number of different environments the hydrogen atoms are in. The ratio of the areas under the peaks will tell you the ratio of the numbers of hydrogen atoms in each of these environments. And the chemical shifts will tell us what sort of environment the hydrogen atoms are in. In high-resolution NMR, what may appear to be single peaks in low-resolution NMR may now appear as clusters of peaks. For example, this and this. This is known as splitting. Splitting gives us information about the number of hydrogens next to the hydrogen atom that we are concerned with. Splitting follows the n+1 rule, which I will elaborate on later. And splitting is actually due to spin-spin coupling between adjacent hydrogen atoms. If you see a single peak, it is called a singlet. If there are 2 peaks in the cluster, it is called a doublet. If there are 3 peaks, it is called a triplet, and if there are 4 peaks, it is called a quartet. There are also more complicated splitting patterns, but this is all you need to know for now. So, what is spin-spin coupling? The protons that are attached to adjacent atoms will affect each other's spin. Let's take a look at the chemical structure of ethyl acetate, for example. There are 2 adjacent carbon atoms with hydrogens that are bonded to them. The protons on CH3 will affect the spin of the protons on CH2 and vice versa. This causes the peaks on the NMR spectrum to split. Now this is the NMR spectrum of ethyl acetate. If you look at the structure of ethyl acetate, we have labeled the protons as HA, HB, and HC. So if we look at HA, the HA protons are bonded to a carbon, which is next to a carbonyl carbon. So there are no neighboring hydrogens on the next carbon. So since it has no adjacent protons, the peak is not split. We see that HA protons give rise to a singlet peak. Next, let's look at HB protons. The HB protons are attached to a carbon, which is attached to another carbon that has 3 hydrogen atoms on it. When there are 3 neighboring protons, then the peak will be split into 4. It follows the n plus 1 rule, so n is the number of adjacent protons and plus 1. So 3 neighboring protons plus 1 equals to 4, and we see that these HB protons produce a quartet split. Finally, let's look at the HC protons. HC protons are next to a carbon with 2 protons. So since they have 2 neighboring protons, they would be split using the n plus 1 rule. 2 plus 1 equals to 3, so they are split into a triplet. And we see that HC gives rise to a triplet peak. Now let's take a look at another NMR spectrum, the NMR spectrum of ethanol. Let's first take a look at the chemical structure of ethanol. There are hydrogen atoms in 3 different environments, one for CH3, one for CH2, and one for the H atom that's bonded to O. First, let me label the hydrogens. So let's name this HA, HB, and HC. The HA protons have 2 neighboring HB protons. So remember the n plus 1 rule. Since they have 2 neighboring protons, it will be split into 2 plus 1 equals to 3. So HA will give a triplet split. So this triplet peak on the NMR spectrum is due to the HA protons. Now let's look at HB. HB have 3 adjacent protons on the CH3. So since there are 3 adjacent protons, the peak will be split into 3 plus 1 equals to 4. So it is split into a quartet split. So here on the NMR spectrum, we see a quartet peak, and this is assigned to HB. Finally, let's take a look at HC, which is the OH proton. Something special about OH protons is that it does not interact with adjacent H atoms to produce any splitting. Therefore, the HC proton gives rise to a singlet peak. Let's also recap a little on what we've seen earlier on chemical shifts. So for the OH proton, it can be found in a wide range of chemical shifts between around 1 to 5 ppm. So this HC peak is within the range. If we compare the HB protons to the HA protons, the HB protons are bonded to a carbon atom that's next to the electronegative oxygen. So the HB protons would have their electrons pulled a little bit further away from them, therefore they are more deshielded and they will appear more downfield. In comparison, HA atoms are further away from the oxygen atom, so they are less deshielded and they will appear more upfield compared to the HB atoms. If we were to look at the ratio of the area under the peaks, we would also find that the ratio corresponds to the number of hydrogen atoms. There is one HC atom 2 Hb atoms and 3 Ha atoms. So the area under the peaks would be in a ratio of 1:2:3. We have just seen the NMR spectrum of ethanol, and we can see that the OH group or alcohol group is an exception to spin-spin coupling. The OH group of alcohols can be found in quite a wide range of chemical shifts between 0.5 to 5.5 ppm. The OH group may appear as a broad singlet, but it can also appear as a sharp peak, as what we have seen in the previous NMR spectrum. The chemical shift of the OH peak can change depending on many factors. One interesting thing that we note is also that the H atom on the OH group usually does not interact with adjacent hydrogen atoms to cause any splitting. That's why we always see it as a single peak. This is because number one, the H atom on the OH group can form hydrogen bonds. Secondly, the OH proton is exchangeable, meaning that the H atom can leave the OH group and another hydrogen can come and take its place. NMR gives us a lot of information of the chemical structure of the compounds. So NMR is a very powerful technique to characterize the exact chemical structure of a pharmaceutical compound. Another application of NMR is quantitative NMR or QNMR. We haven't discussed this in this chapter, but just know that there is such a thing as quantitative NMR, and it can be used to determine the concentration and purity of compounds. An advantage of quantitative NMR is that it does not require any chromatographic separation prior to the analysis. So for example, it can be used to determine impurities without needing any prior separation, and it can also be used to analyze drugs in a formulation without doing any prior separation. Finally, let's take a look at the strengths and limitations of NMR. The strength for NMR is that it provides more info on molecular structure compared to any other analysis technique. However, the limitations are that firstly, it is relatively insensitive and requires quite a lot of sample. So for proton NMR, at least 5 milligrams of sample is required. For carbon-13 NMR, at least 20 milligrams of sample is required. NMR is also a very expensive instrument, and it requires its own special lab as well as a specialist operator and regular maintenance.